Okay, so today we will talk about transistors, and this will be our final lecture about electronics. So, transistors. We had our lab works, and now we'll try to cover what we did there, and we will learn the theory. So last time we talked about semiconductor diodes. So diodes were made of one p-n junction. So diodes are basically one p-n junction made of p semiconductors, p semiconductor and n semiconductor, which has positive conductivity produced by holes and negative conductivity produced by electrons. So transistor is made of two p-n junctions, and it can be NPN transistor or PNP transistor. So it can be represented like this. So during lab works we had NPN transistor, but transistor can be PNP. The working is the same, but only the connections change a bit. So it has, every transistor has three terminals, as you can see here. It is emitter, base and collector. Emitter, base and collector. So E stands for emitter, B stands for collector, sorry, B stands for base, C stands for collector. And you can see them here, EBC. So NPN transistor is in a circuit. It is represented with this notation. So it is represented like this. This is NPN transistor with arrow pointing out. So it is collector, emitter and base terminals. And there is also PNP transistor. It is the same, but the arrow is pointing inwards. This is regarding the direction of the current flowing. We will see this later. And every transistor has three parts or three terminals. Those terminals are emitter, base and collector. So now there are three possible connections of transistor. So or in different words configurations. So first is common base, second is common emitter, and the third one is common collector. Common base configuration is used when we need to amplify voltage. So in this, when we use this configuration, we get voltage gain. This common emitter, it amplifies both voltage and current. Common collector amplifies only current. Common emitter configuration is the most used. This is used sometimes. Common collector is very rarely used. So we're going to cover this one and this one. Okay, so to understand the working principles of transistor, it is good to start with common base. So we can common base configuration. So common base. Here we will have NPN transistor. So we can draw the transistor, and maybe we can start from I will redraw this a bit. So common base. Okay, so let's draw like this. Base is very small compared to emitter and collector. So we have E, B, C. So let's have NPN transistor. So this means there are a lot of electrons here. Here there are a lot of holes. Not a lot of, but some. As compared to others too. Here we have electrons also. So this will represent our transistor. Emitter, base, collector. So common base. So it means that we will have two wires coming to base. Two wires joining together and coming to base. Okay. So these are one wire, another wire, and they join together to go to base. So here we have VB. This is base voltage. VB is base voltage. Here we have voltage supply that produces higher voltage. So this is collector. This is collector voltage. It is VCC. Collector voltage. higher than VB. Now this is R0 base resistor. R0 stands for, or it's not base resistor, it's called, maybe it's better to call it's here near emitter, so maybe just call it emitter or input resistor. Why? It's not, definitely not base resistor, but it is input resistor can be called because input signal is given here, as we here have the terminals, and we can write it here, it is input. So here the signal that we want to amplify comes, voltage that we want to amplify. This is RL, load resistor. So load resistor. Okay, and here it is output signal. Here goes the output signal. In this case it is output voltage. Okay, so now what is happening here? When there is no this part, so we can have only VCC, RL, and base and collector. So we can see that base is positive here and is connected to the negative terminal. So N is negative, it's connected to the positive terminal. So this corresponds to a diode. Now that is, so diode is made of these two, base and collector. Diode is made of and this is represents a reverse biased diode, so it means it's not working, so no current is flowing. When we turn VB, so then what happens? These electrons that are here, they go to this base because they are attracted by this positive terminal of VB. So they go here, but because there are too few holes in this base, the electrons, some they recombine with these holes, but most of them they come and they stay here. So electrons, there are a lot of electrons that come from emitter. So emitter, it injects electrons, so that's why it's called emitter emission. So injects electrons to base, and then these electrons are caught by the electric field of this VCC. So these electrons that are in red, they are attracted by this positive terminal. So these electrons, they move to collector, and that's how the collector current is produced. So the currents flowing here are this, so electrons flow that way, but as you know, the direction of the current is opposite. So here we draw collector current. Emitter current is electrons are flowing here to this direction. However, we make it emitter current in reverse direction, so because that is the rule. This is base current going to this direction. So 3 currents. So you know what happens now. Emitter has a lot of electrons because this is connected in so that this PN junction is biased forward. So those electrons that are here go to the base, they enter the base, and then they can be attracted by this positive terminal of collector voltage supply, and then they make this collector current. So electrons enter here, some they recombine with holes, but there are too few holes for all of them to recombine, and they move here, practically all of them. And some of and the leakage, very small leakage of these electrons that don't go here, don't make the collector current, they make this base current. So as I say, these electrons, all the electrons emitted from emitter, they end up creating collector current. So we can write that emitter current is almost equal to collector current. This is almost equal to. So now what is the voltage drop? Voltage drop on this R0. Voltage drop on this R0, it is what? It is voltage drop on R0 is emitter current times R0. Let's make it U0. Now voltage drop on RL on load is what? It is the IC times RL, sorry, and it is UL. So now this K, it represents the ratio of UL divided by U0, and it is what? UL IC RL IE R0. Because IE is almost equal to IC, so we may cancel these out, and we can write that RL divided by R0. We can write that K is equal to the ratio of RL divided by R0. So when and probably also always when RL is adjusted to be much greater than R0, voltage is amplified. We get the voltage gain, and as this ratio of RL and R0I increased, so it means that RL is adjusted to be higher compared to R0, we get a higher voltage gain. So this is, input voltage is given here, output voltage is measured here. So this is how the transistor works with common base configuration. Now we can go to common emitter configuration. So common emitter configuration. It means that we have we connect emitter with base and with collector. So we also draw RL. This, maybe let's draw this. Base is small. Emitter, base, collector. We have NPN transistor. So this is connected. Here we have this should be shorter. And this, let it be our circle, a bit with deformity, but nevertheless. So this is VCC plus minus, this is VB minus plus. Now what? This has a lot of electrons again. This has holes. This has electrons also. So input signal is given here. Output signal is measured here. Again, emitter base junction is forward biased. It is forward biased. Now when it is forward biased, electrons are attracted by this plus and they move to the base. In base some of them recombine, but most of them go to collector and they produce collector current. So the working principle is the same as it was before. So here we have three currents. So one current that is going through this load resistor, it is collector current. Another current that it is going through base resistor, it is base current. And another one, it is the emitter current. It is going it should be go from plus to 0. So it is going into this direction from plus to 0, from plus to 0 here, and it is going to this direction. So it diverges. So it is emitter current. So this time currents are measured at base and are measured at collector. Last time, previously, the voltages were measured where? At the emitter and at collector. So this time we're measuring base current and we are measuring collector current. What happens here? As I told before, that IC is almost equal to IE. So in general, emitter current is IC plus IB, but can write this like this, EIC. So these are almost equal because base current is small, so it means that IE is equal to IC, because this is negligible. So because we are measuring currents we're measuring conductor current and we're measuring base current, so IC divided by IB is beta. So this is high, this is low, and this produces some current gain. So it means that we get current amplification. So this is the simple explanation behind all those complex equations, and we can derive some anyway we can derive some equations here. I will try to show them to you. Just zoom out a bit. Okay, so we have this. Now what's going on? One equation is IB. IB is equal to what? As you can see, this IB maybe we can write like this: IB times RB. This is voltage drop here on this RB. It is equal to voltage of the base voltage. So VB minus voltage. Where else can the voltage drop? It can drop here on this emitter and base junction. So VB minus VBE. So this is the equation for voltages. Now I can divide both sides of this equation by RB, and I get what? I get IB VB minus VBE divided by RB. Now another one equation, it is for this part. So I can write IC times load resistance. So voltage can drop, voltage in this part from VCC can drop on ICRL. So VCC minus and collector emitter terminals. It can drop across here on these both PN junctions. So VCC minus VCE. So this is the equation for this upper part, this voltage supply. So now again I divide by RL and I get IC VCC minus VCE divided by RL. So this is collector current, this is base current. So, and these currents, they are joined by equation IC divided by IB is beta, by this equation. In other words, IC is beta times IB. So here you get three equations. So three equations. Which first one is for what? It is for RB, for this part of the resistor, lower part, lower circuit. This base voltage, it can drop only on two parts. It can drop on resistor, base resistor, and it can drop on this emitter base junction. So it can drop either here or there. So it sums up. Some voltage drops here, some voltage drops here. So VB minus VBE is IB times RB. Again, this voltage, total of this voltage, can drop on this resistor and it can drop on these two PN junctions, EB and BC. So in general on EC. So we write like this: VCC minus VCE is ICRL. So, and for currents we get this relationship as for current gain. Alright, so now we have covered these equations. Now there are two possible ways to use transistor in common emitter configuration. So these ways are to use this transistor as an amplifier, or to use the transistor as a switch. So transistor as amplifier. So when we speak about transistor as an amplifier, we usually talk about volt ampere characteristics of a transistor. So we can discuss it together. So during laboratory works, we have determined the output characteristics of transistor. That means we have the IC. It was in microamperes, and here it was VCE, voltage of between collector and emitter, and it was in, let's write it in volts. So we determined this relationship. So in general it looks like this. This. So okay, so this is for IB1, let's say it was 5 microamps, IB2 10 microamps, IB3 15 microamps, IB4 20, IB5 25. So these are base currents. So this, let's say it is equal to 2000, this can be equal to 4000, this can be equal to 6000, this to 8, and this should be equal to maximum 10,000. Okay, 10,000. Now this is voltage drop on collector emitter, between collector and emitter, and this can be, maximum can be here, and maximum can be equal to VCC. We cannot get more voltage that we get on the collector supply. We cannot get any more voltage. And for transistor to work as an amplifier, VCE is said to be half of VCC. So so it means that if we have VCC 3 volts, it's equal to 3 volts, because during lab works we had this is just an example. So we take half of this and we have here, so here it is half of VCC. Half it means 1.5 volts. 1.5 volts. Now why is this? This comes from the equation IC times RL. It is VCC minus VCE. So it means that we adjust this VCE to be a half VCC. So why it is that? Because when we use transistor as an amplifier, so amplifier, it means IC is IB times beta. So here we have IB 5 microamps, 10, 15, 20, 25. So IB is multiplied in this case by 400. So 5 times 400 is 2000, 10 times 400 is 400,000. So in this case beta is 400. So IC increases. IC increases. And this equation here, it represents the voltage drops. So because IC increases, so this IC increment has to be produced by some voltage. So that voltage is taken from where? If you want to increase IC, then it means you have to increase the voltage drop on this voltage drop that is on the load resistance. As you go back to this circuit, you will see that when we derive this equation, if we want to increase IC, we need to also increase voltage drop on this RL. So it means that we need to do what? We need to get some voltage from somewhere. So we can get voltage only from VCC. And how can we get it? We can only reduce the voltage that is on VCE. So in order to produce IC, we need to take some voltage, and we take the voltage that was on VCE. So this increment in the voltage is produced by lowering the voltage drop on VCE. So when we lower the voltage on VCE, we go to this part. From VCC we go to this part. To this part, to the left. So when IB increases, IC increases. We see in this equation IB increases, IC increases. So then what happens? IC RL, that is the voltage drop on RL, it also increases. And it means what? It means that VCE, because this increases, VCC is constant, so it means this has to decrease. So VCE decreases, and from a half we go here. So we need to preset this VCC equal to a half, to VCE, initial VCE to be equal to a half, in order to be possible to achieve high currents. Because we need some remaining voltage to take from VCEs to get those current increments. In other situation, when EB decreases, so what happens? IB decreases, IC decreases, ICRL also decreases, and what happens with VCE? VCE increases. So we go to this part, VCE increases, so this means that the reduction in collector current, to get this reduction, the voltage must go somewhere. So to reduce this collector current, the voltage goes to VCE, and we are in this part of the axis. So initially positioning us at a half, it allows us to obtain increase in IC and decrease in IC, because as base current can swing up and can swing down, by positioning at the half we are able to register IC increase and IC decrease, so we don't lose neither this increase or decrease in the current. So if it's the base current in time, if we get this swing, let's say to 10 microamperes, and we get a reduction in minus 10 microamperes. So in one case we get amplified collector current, in another case we get decreased collector current. So but usually this swing is put on some DC line, so we can talk later. So that's only the explanation why we take half of this voltage. Now this when we say this voltage, this voltage is always in the so-called linear, maybe like this, linear region of the transistor. So it is like this region, linear region. It means that these curves are equally distributed. As you can see, they are nicely equally distributed, these black curves. So it means that this linear region is represented by this equation. IC is beta times IB. So it means that we know by the equation of a straight line y is kx what is the amplification, and if we took those IB and this IC to make a graph, so let's do it. So we take IB here, IC here. So in microamps there were 5, 10, 15, 20 and 25. Here we get what? Here we get 2000, 4000, 6000, 8000 and 10,000 in microamps. And this comes to, at 5 we have 2000, at 10 we have 4000, at 15 we get 6000, at 20 we get 8, at 25 we get 10,000. It is almost a straight line that we get. In practice we should get this straight line, and this alpha, this tangent alpha, is equal to beta, as it is like this. So this is linear region. It means that between IC and IB there is a linear relation. And now to, as I told you here, this, how to select the base current, base current is usually selected like some positive value. So it is selected like this. I will probably try to make like this. It is selected some positive value. So let's say it is selected 15 microamps. Let it be selected 15 microamps, and then the positive swing to 20, and here negative swing is, it doesn't go to minus, it stays in the positive, because these are positive. This will be IB. So this is DC part of IB, some DC part that is constant, that we need to pre-select, and this is the input signal. Input signal develops, this is AC part plus DC, and this input signal, it develops on DC part. So this is done in order not to get this minus, as I show here. This is minus, but usually it is done here because it's more convenient to make this kind of circuit. So how to select this DC these 15 microamps? How to select these? So usually how it is done like this. We take we draw a straight line. We draw a straight line, and the straight line is drawn on maximum collector current. So IC max, it is taken by VCC divided by RL. So in this case we can take so it is on at VCE 0. So it is from this equation. So one one position is here. We can mark it with X. One position is here at 10,000. Another position is here. So this is at IC equal to 0, at VCE equal to VCC when VCE is 0. When VCE is 0, everything drops on RL, and it is at IC is 0, everything drops on VC. Sorry, at IC is 0. At IC is 0, everything drops on VCE, because here drops nothing and everything is, all the VCC drops on VCE. Here VCE is 0, everything drops on the load resistor. So here we make here X, and now we need to connect these things. And we see that, where did we obtain, and then we select the point on this load line based on this half. So the point is here, so at 10 microamps. So we can collect this figure to say that it's 10 microamps here for us. This not very nice representation. You can maybe not nice drawing, because this is very complex, so you can find it on lab Word file that I have uploaded. But basically the general concept holds here, because here you get 1.5 volts here at this Q point. This is called Q point, the working point of the transistor operation point or quiescent point. This word is Q, quiescent point, or Q point, or transistor operation point. So it tells you at 1.5 volts you take 10 microamps DC base current. You develop AC current on this DC current at 1.5, so to get positive and negative AC swings on this base current, and to produce collector current increasing or decreasing. Okay, so this was very complex theory behind transistor as an amplifier, all transistor volt ampere characteristic, because you see it's a lot of involved here. Now another thing, it is transistor as a switch. It will be it will correspond to this very much. So transistor as a switch. Transistor as a switch. Here I will need to draw this again, and here we have, in this case, we have the same. We have the same volt ampere characteristics. They should be equidistant. They don't look like so now, but maybe we can make them look like it. Now I spoiled the thing. We can try again. We can try again. So okay. Now it comes denser and denser. So maybe I will just switch to this drawing that I have, and it's difficult to draw these days. So we have this transistor volt ampere characteristics, and what we get here, we get as a switch. So transistor as a switch, transistor as a switch. And we don't need these values, neither these nor these. We just need to see how it looks like. So this corresponds to different base currents. So as you can see, there are two squares here. One is this white square. This is also grayscale, but it's in darker color, so you can see. So this part, this lower part, it is called the cut-off region. This is this white part here, all this at zero on y-axis. This dark gray at 0 in x-axis, 0 x-axis is here, so it is here, very close here. So it is called the saturation region. Saturation region. So so what happens here? This saturation region is produced where? At saturation. At saturation happens what? So at saturation, IC is equal to IC max, and it is equal to VCC divided by RL. So it is like previously. And also what happens here, and also VCE is 0 volts, theoretically. Theory. Now in practice, what happens in practice? In practice, this VCE is equal to VCE saturation. Saturation. SAT, saturation. This is low voltage. In our lab works, we could get 40 millivolts, so it is low voltage. So it is close to 0 in theory. This VCE is equal to VCE saturation. Now in this cutoff region, what is in cutoff region? So at saturation we have one conditions. Now in cutoff, we get what? We get an IB here is above 0. At cutoff region, what is this? Cutoff 1T, cutoff region, we have IC equal to 0. So it means that VC is equal to VCC and IB is equal to 0. So two situations. So when using as a switch, the transistor has to be either fully on. So fully on it is here. So we don't want any intermediate currents. So we need either the device working, so it means that when the device is working, when IC is max, so it is working, so it is on. So on conditions. Here these are off conditions. The device is not working, no IC. So transistor operates between its fully on and fully off conditions. So between its border conditions, we can say. So what happens in these conditions? So probably what happens at saturation conditions. So in saturation conditions, you can see that here what happens. When IB increases, here it is increases, but here we are in saturation. IB increases, and we can see in this part, IB increases, and then we cannot diverge between IC here. We cannot diverge between IC. So it means that the same IB this or IB this, it gives the same IC values. So we cannot diverge. So it means at saturation here, the relationship IC, IB times beta is not valid. And it means that at these conditions, we can draw a graph. Here it is IB, here it is IC, and we can see that it's going like this, and then it is saturating. So this is microamps and this is microamps. So this is at this is VCE. So this collector current stops to increase when when base current is increasing. As base current is increasing, collector current stops to increase when saturation voltage is reached or adjusted. We can say that adjusted. So it means that at VCE equal to VCE saturation, the base current does not control collector current. So it means that there is no longer amplification, amplification of base current. So here transistor operates between its two terminals. And now we can go back to this to zoom out a bit. So here's what I've written, and So you can see, and you can get, and this is the I don't know how to put this in one page, maybe like this, and you can also have these probably better representations. Because these drawings are rather complex. So you may have, now it's completely out of focus, you may find better in LabWorks, in Word files of LabWorks. Where you can see the transistor used as a switch. And in one case it's operating fully on. In one case it's operating fully off. So here's these are the situations. This we don't need. So these are two cases. So cutoff region and saturation region. You can also take a closer look at this. I will try to zoom a bit. If you want to look at this picture, and this is final thing that I wanted to tell you about electronics, and I will produce questions and cover them in the next lecture. So good luck for now.